Okay, so the first talk we have Ben Chaffin from Ampere. He's gonna tell us about the memory tagging work that Ampere is doing. He's an SoC and performance architect for Ampere, and he's been with Ampere for 7 years. And before that, he was at Intel, also as an architect. Go ahead. Actually, let's welcome him. Sorry.
All right, good morning, everyone. Yeah, I'm Ben Chaffin. I'm in the architecture team at Ampere, and I'll be talking about our implementation of memory tagging in the AmpereOne processor. As we all know, a modern CPU project is a massive undertaking, so of course the design I'm presenting here today is the work of many of my excellent colleagues at Ampere. So what is memory tagging? It's a powerful hardware and software feature to detect and also mitigate memory safety violations, things like buffer overflows, use after free, stray pointers. Anytime you're dereferencing a pointer or accessing memory that you didn't intend to or aren't supposed to, but at a finer granularity than page-based protections, and even when that memory belongs to your own process, so it's not a traditional privilege violation. The way it works is that each 16-byte granule of memory gets a 4-bit allocation tag. So that's a 4-bit value that's physically associated with that piece of memory. And then pointer variables carry an address tag in some of the unused upper bits of the virtual address. And then on every load and store instruction, the hardware compares the allocation tag and the address tag to make sure that they match. And if they don't match, that's a tag mismatch error. You can silently log it for later inspection. But if you want to actually rely on memory tagging to prevent these bugs, and if you want to find where the bug occurred, you want the synchronous faulting mode. In that case, you get a fault on the access with the tag mismatch, very similar to a page privilege violation. The access doesn't complete, you immediately go to an exception handler. Our implementation is completely focused on the synchronous tag checking because that's what allows you to actually block bad accesses. Ampere is focused on data center SoCs, cloud machines. So those have unique capabilities and also unique requirements compared to a client system. First of all, memory capacity and cost is probably the most important factor driving the design of cloud platforms. Any reduction in memory capacity directly affects the total cost of ownership of that system. And if you want to carve out a chunk of your DRAM to store your tags, that's going to be about 3% of your DRAM. If you have terabytes of DRAM installed in your system, that's expensive. For cloud servers, also memory reliability is non-negotiable. That directly affects the cloud service provider's ability to deliver reliable services to their customers. So comprehensive RAS features, error correction, symbol ECC is the Ampere's proprietary version that's similar to chip kill or many other technologies from other companies that detects multi-bit device level failures. Those are essential features, and you can't compromise there. And finally, multi-tenancy. There's typically many guest VMs running. The architecture of memory tagging requires that if tagging is available, then it's enabled for all of physical memory, but it may be that not all guests are using it. So those things drove the kind of key design goals that we were aiming for in our implementation. First of all, minimize or eliminate the memory capacity overhead of or impact of tag storage. Focus on synchronous tag checking with as low performance overhead as possible, and minimize the performance impact of the availability of tagging on software that's not using it. So those requirements led us to this design. The central tenet of the design is that tags travel with and are co-located with data throughout the entire memory hierarchy. So starting all the way out at DRAM, tags are stored by repurposing some of the ECC bits, but through our own custom ECC algorithms, we're still able to deliver ECC correction, detection and correction that meets the requirements of cloud service providers. And these systems are in deployment in production with memory tagging enabled. So that's true. So we support SecDev ECC with 128-bit granularity, but the more commonly deployed setup is symbol ECC. And that provides 100% detection, 100% correction for bounded faults, and nearly 100% correction for unbounded faults. Coming out of the memory controller, the tags flow with the data throughout the mesh. They're stored in the system level cache. They flow into the core with the data where they're stored in the L2 and L1 caches. And the tag checking is done directly in the L1 pipeline in parallel with address translation and cache lookup. So that means that for loads, there is absolutely no performance impact to tagging. If you have the data, you have the tags, and the tag checking is done on the side in parallel. So load behavior is not affected at all. Stores are a different story. When tagging is enabled, they request their line at address translation time as soon as possible, just like a load. And just like loads, that early fetch can often hide some or all of the memory latency behind the out-of-order execution of the core. But stores can't commit until they've performed their tag check because they might have to fault. And so that's the main source of the MTE performance overhead in the core, is the delay of store completion. I want to call out store forwarding as a particular challenge for correctness. And I know that some implementations of MTE just disable store forwarding for tagged memory. But we really wanted the best possible performance with synchronous tag checking enabled. So we do support full performance L1 latency store forwarding in the common case where the tag of the store and the load that is forwarding to match. If the tags don't match, well, they can't both be right. One of them's going to fault. So we don't allow forwarding for correctness, but also who cares about performance because you're just about to take a fault. So the end result of that co-location of tags and data through the whole pipeline means that there's no capacity cost. You don't have to give up 3% of your DRAM to store tags. And there's minimal bandwidth overhead. We never have to access two different physical addresses to collect the tag and the data for a single memory access. In a many-core cloud system, bandwidth is a precious resource. So that's a really nice selling point, that we don't have to duplicate accesses for tag fetch. Okay, like I said, this silicon is in production. So we did some performance evaluation on this set of workloads. We have 4 different databases: web server, video transcode, and spec. All of these workloads, we've done a lot of tuning of them internally. So the baseline performance for all of these is not just out of the box. This is the best known configuration for this workload that gets the highest throughput out of the whole system. The setup is an AmpereOne X platform that's 192 cores with 8 channels of DDR5. And we're looking at 3 configurations. The baseline configuration A is just no MTE. B is MTE is enabled, but not being used by software. And then C is MTE is enabled and the software has requested tag memory and tag checking. So B versus A, that's the impact of the cloud provider of making tagging available to their customers. And there is some performance costs, as we'll see there, because we have to preserve tags when memory is modified. And then C versus B is the cost to the end user of, if you want to get the benefits of memory tagging, this is what it's going to cost you. Okay, enough talk. Show me the numbers, right? Okay, there's a lot of data on this slide. Let me see if I can get the laser pointer. I'm not going to talk through everything, but we have on the left, we have the non-spec benchmarks. On the right, we have the breakdown of iSpec. So first, let's look at the B versus A column right here. So several of the benchmarks see no statistically significant difference in performance. There's a few losses in the 2 to 5% range. Memcached actually gains significantly from a prefetching effect of tag reads. It feels like a microarchitectural feature waiting to be born. And likewise on spec, although looking at B versus A, it varies by workload, but the average is about 1.5%. So typically in the sort of 1 to 2% range for making tagging available. Looking at C versus B, so this is actually enabling tag checking. Likewise, several workloads see no significant difference, about a 5% loss on video transcode, another small gain on Nginx. Looking at spec, many of the benchmarks don't care too much, but as you can see, there are some notable outliers, in particular GCC and Xilinx, also Perl and Omnet. I should mention, this is a first-generation hardware design. We learned some things along the way. There is definitely at least one performance bug that was not found in time to be fixed. So there's I think, significant room for improvement in the hardware overhead here. But as we'll see, the sort of internal implications of tag checking are not the only thing contributing to performance. So we wanted to understand those 4 spec outliers and what's going on there. So we did an extensive debug into those. And we diagnosed the performance loss to 3 primary factors. First of all is eager tag initialization. GCC and Xilinx in particular, they allocate large blocks of memory that they never use. And without tagging, those pages are never touched, and so they're never instantiated. They don't really exist. But with memory tagging, as soon as the allocator gets the memory, it goes through and it writes to every line in that page to initialize the tags, creating a whole bunch of excess bandwidth. And because it's spec, which we love, and we're not doing rolling round robin yet, those spikes in bandwidth tend to occur from all cores almost simultaneously, which is the worst case for SoC performance. Second thing is increase in committed instructions. We're just running more code. We're doing more stuff with tagging enabled, and that comes from two places. First of all, to get tagged memory, you can't use break to extend the heap. You have to use mmap, and that's a more expensive system call. And also malloc and free just add some work to manage tags, to set and clear the tags on every allocation in free. And finally, the applications that do lots of very small, short-lived allocations are the ones that see the biggest impact. Of course, if you're just calling malloc and free a lot, that's going to magnify the impact of extra instructions on those paths. But the spatial pattern of allocations matters too. Perl does lots of small allocations, but it tends to free things in the same order they were allocated. Whereas GCC is building a big tree structure and its allocations are all over the place and they're freed out of order and so forth, resulting in a fragmented memory map, which then increases the cost of later mmap calls because it has to find a suitable block of unused virtual address space from a large fragmented map. GCC also calls realloc a lot, which if it has to move the memory, has to move tags as well, which is some extra cost. We tried running the spec with JEmalloc, which is a different allocator library optimized for small allocations. And you can see on the bottom right there that all of the benchmarks which are most affected by MTE also gain a lot from JEmalloc. So that kind of backs up the theory that these small allocations are an issue. Now, I'm not a software expert and I don't have a slide on here's what we should do, but you can feel there's some room for improvement or sort of co-design here. You could imagine things like the allocator could maintain pools of pre-colored memory, or the kernel could allow the allocator to somehow between the allocator and the kernel, they could enable lazy initialization of tags. The kernel could supply 0 pages that already have a particular tag applied so that you don't have to initialize the tags on the first touch of a page, or at least so that the tags aren't initialized until the page is actually touched for the first time, rather than doing it immediately at the beginning. But the key, there's going to be a performance overhead for tag checking. There's no way around that in the hardware. I mean, the hardware is doing more work than it used to. It's waiting for things it didn't used to have to wait for. There's always going to be an overhead. But that overhead, the overhead of tag checking itself, seems to be relatively small, typically just a few percent, and sort of across the board on workloads. The key discovery through this debug was that the more dramatic performance outliers are driven more by the interaction of software with the tagging feature than by the kind of hardware fundamentals of doing tag checking. And that means there's opportunity for optimization and improvement there. Okay, so to wrap up, MTE, I love MTE. As many of us, I'm sure I have lost weeks and months of my life to finding pointer programming errors in my own code. And MTE offers a way to, sanitizers work, but they're slow and they require recompilation. And MTE offers a way to find those bugs in a production environment at full speed and to offer ongoing protection for real systems that are running all the time. The architecture does not specify how tags should be stored and accessed. That's up to the implementation, and those implementation choices make a big difference for the performance. We chose to co-locate tags with the data throughout the whole pipeline. And we think that obviously that doesn't work in client where there's no ECC bits, but we think that for servers, that's a great implementation because it allows us to deliver well-performing, precise tag checking on both loads and stores with no capacity overhead, minimal bandwidth overhead. And finally, obviously, there's been a lot of great software enabling work already just to make tagging work through the allocator and the kernel. But it seems like there's room for further investment in MTE-aware allocators, similar to what Apple's done with MIE, to really address some of the more significant performance impacts and make MTE even more attractive as an always-on, always-deployed safety feature in the field. There's more details in the paper, link right there. And that's it. So we can take some questions now.
Great. Hey, great talk. I'm Trey Kane from NVIDIA. I share a lot of your enthusiasm for this feature. Can solve a lot of problems. At the same time, given that, ARM doesn't make this a mandatory feature, a lot of companies are kind of playing wait and see here. I'm curious about the thought process at Ampere and what made you guys decide, now's the time, we're going to do this now.
It's just so cool. I mean, why would you not do it, right? Like, how could you say no, even though it's an optional feature? The other thing is, and this is, Oracle has publicly announced, I mean, they're using this in their deployed systems. They're using it for their internal database. They were a big customer of ours and they wanted it. So we're responsive to our customers. Yeah, so that was the driving force. We had a big customer who was really excited about this. Of course, Oracle owned Spark before that. They had ADI. Spark went away. They lost ADI. They really wanted it. They really wanted it back. So that was kind of the animating force.
Got it. Thank you.
Yeah.
Great talk. Thank you. I'm Sergio Schuler from ARM, but a while back I was at Spark working on ADI.
Oh, nice.
So I love MTE. I love it ADI more. Why 16 bits per 64 bytes instead of the Spark implementation that had 4 bits per 64 bytes? What is the advantage? It seems 16 bits is rather a heavy penalty to pay.
Yes. Well, you should ask ARM about that. I mean, that was not up to us. That was the architecture, right, as specified. But we did push back on it a little bit early. If you're not storing the tags in ECC, you have to store them in DRAM. So there's a balance between, if you do coarser tagging, as ADIs, I think it had a tag per cache line, right? Then you have to increase the minimum size of your allocation to get tag coloring. And that has that wastes memory, basically. Your small allocations grow. Smaller granules increase the tag storage cost. I think, the 16-byte granule was trying to balance the cost of tag storage versus the capacity cost of having to do a minimum 16-byte allocation. So,
thank you.
Yeah.
Hi, thank you very much. Jourdan from University of Pennsylvania. I have a question regarding, it seems like most of the tagging that you've been described is based on a heap. And I'm wondering, have there been any security evaluations based on the tagging that you have implemented on, if there's any CVEs that you could have been blocking are now being blocked with these? And could you comment if there's any need to tag beyond heap? Let's say people want to be interested in stack-based protections and whatnot. And I guess there's a second question I have about, you talk about these MTE aware allocators are essential for the next step. So could you comment on how much of the, I guess, software efforts or code change that was needed to be able to enable MTE tagging for these like natively not MTE aware software?
Okay. All right, let me tackle the second part first. So software typically does not need to be changed at all to work with tagging. It needs to be relinked. Right. So the allocator library needs to be changed. So you need to relink with that allocator. But the software itself doesn't need to be recompiled typically. I think tagging the stack is interesting. That will require recompilation because you have to change the way your pointers are managed. So that's kind of a next step. But I think, obviously stack overflow based attacks are common. And so, yeah, I think there's room there. And there's no fundamental reason that memory tagging can't be used on stack memory. It's just more complicated. I don't have the details in my head, but in the paper, we quote a bunch of stuff, including from Microsoft, about how many CVEs could have been prevented with tagging. And it was a substantial fraction, like many of the already known, memory safety type CVEs would have been blocked by tagging. So it would have been effective in those cases.
Right. I think the reason I'm asking is understanding that the MTE tagging have a limited number of tags, right? So there's some probabilistic protection. So yeah. I'm trying to understand, at this granularity, because the performance is very related to how fine grained you're tagging, right? And was this kind of granularity, how realistically, how many attacks were able to stop?
Yeah, so for sort of random accesses, yes, it's probabilistic. For sequential accesses, it can be deterministic, right? As long as your allocator is smart about assigning tags. So
Thank you so much.
yeah. It caught bugs in the spec code. Yeah.
Thank you so much.
Yeah, you bet.